Welcome, everybody. We're here to listen to Bill Menasco tell us about the Seifert algorithm for integral homology spheres. Bill, take it away.
Well, thank you very much. Thanks to the organizers. This has just been a kind of a really interesting exercise, going all these talks. Unfortunately, I've missed a lot because of times and teaching obligations. Um, but this is not too deep. This is kind of low technology I'm going to talk about. A Seifert algorithm for homology spheres. This is joint work that I did with my student Linda Algura. And where is it? How do I advance this thing? There we go. So this is a screenshot that I took of paper by Herbert Seifert that appeared back in 1934. It's about the first paragraph or so. Um, and in that paper, it was a seminal paper. He, gives a very simple algorithm uh, for given a regular uh, projection of an oriented Noether link on a two-sphere in three space in S3. And he's that algorithm, it yields an oriented surface that you can think of it as overlaying the knot projection. Um, and so it produces a surface. He also in that paper, he it takes that surface and produces a matrix from that surface that kind of inscribes the homology relations that are going on. And then from that matrix, called the Seifert matrix, he gives an effective method for computing the Alexander polynomial. And then he did a bunch of other things in the paper. He demonstrated that half the degree of the Alexander polynomial was a lower bound for the genus of the Seifert surface. A really nice piece of geometric algebraic topology. And he does further investigation about the structure of the polynomials coming out of the Alexander polynomial. And in fact, he gave examples of non-trivial knots that have trivial Alexander polynomials. So, and in so many ways, a pathfinding paper. You think about the knot theory that has gone on in terms of how we just can start doing calculations given a knot projection. This was kind of maybe the first instance of some really deep calculations that can be made. So just a brief reminder of how um, this construction goes, because I'm actually going to try to play off of it. So you're given a knot projection. So here on the left, I've got the oriented knot. You smooth the crossings and you get a bunch of circles. And since this over here is a planar graph, you end up with disjoint collection of planar circles, and they're oriented. And the orientation is induced by the orientation that you have over in the original projection. And you cap each one of these circles off with a disk. And I'm going to think of it bulging towards us, from the projection plane. And so these disks can be nested, and the disks are oriented. They get the induced orientation coming from the orientation of their boundary. Then you recapture the original knot by putting in these half-twisted bands, one at every crossing that you smooth. All right. So it's of a fairly elegant and simple algorithm we can teach high school students. That's fun to play with. But the game plan for this talk is I'm going to try to repeat that calculation, but the starting point is in fact an oriented link inside a homology sphere, integral homology sphere. And we will just, I want to describe this construction of the spanning surface. So you're given an oriented link, and I want to produce a spanning surface. I'm going to require that at some point I appeal to some projection-based construction where we do something similar to what Seifert did. Um, I got to describe the three manifold. It's going to have a handle decomposition. Uh, and that handle decomposition is going to be captured by a planar graph that I'm going to call the Hagar graph. And we're going to take the knot or the link, and we're going to put it in a normal position inside the three manifold. And when I say normal position, I'm referring back to the handle decomposition of the three manifolds. So it's normal with respect to that. Then when we construct the surface, it will be also normal, almost, all right, with respect to the handle decomposition. And because we're going to get Seifert circles too. I'll put air quotes around the Seifert circles. The almost comes in the fact that at the very end, you have to add the half twisted bands. Uh, so let's talk about this handle decomposition a bit. Uh, uh, Everybody hopefully is familiar with how this works. For three manifold, any three manifold can be built as follows. You start off with a copy of a three ball, and you give it the following structure: a zero ball across a three ball, and that's the zero handle. That's unique zero handle. Then you add to it G1 handles. You attach G1 handles, and the structure of the G1 handles, they're each topologically three balls again, but they have the structure of a B1 cross a B2, so a one ball cross a two ball. The ends, you take the boundary of the one ball and you get two disc ends, and those are attached to the boundary of the unique zero handle. Here I'm using that notation, this bold H of zero, and the three is just the dimension. So the subscript speaks to what handle dimension it is, and the three is just that it's a three manifold. Um, and then onto that, you attach G2 handles. A two handle it has this product structure again, but it's reversed from what the one handles were. Two handles are two disc cross B1s, and the attaching is you take the the boundary of the B2, which is a circle and cross with a B1. So you end up getting an annulus, and you're gluing it to the boundary of the one and two handles, the boundary of the zero and the one handles combined, which is that boundary is a genus G surface. Um, so when I teach this, I usually like to think of one handles as being Pringle cans, and two handles as being tuna cans, and you're gluing the top and the bottom of the Pringle cans to the boundary of your zero handle, and you're gluing the label of the tuna cans to your genus G surface. And then you do this right, uh, uh, you end up with your zero, one, and two handles all combined to an object that when you take its boundary, it's a two sphere, and then you cap it off with a three handle. All right. So the Seifert algorithm that we're going to do is if we go back and look at it at this, this um, regime of a handle structure. If you go back and look at S3, it also has a handle structure, but there's no one and two handles. There's just a zero handle and a three handle. And uh, if we're interested in more interesting examples, then we have to add, we have to think in terms of three, of one and two handles. Um, and let me give you an example of how this can be seen, and I want it all encoded in a graph, this Haggard graph. And this comes from, this example comes from Dale Rolfson's Knot and Links that is in there. Uh, this is a fat graph, or a graph with fat vertices and then edges coming out of them. And the fat vertices are uh, disk regions. They occur in pairs, and the perspective that you should have is that we are when you're viewing this, you are inside the zero handle. So you're inside a three ball, and you're looking at its boundary, and you see these pairs of disks, um, that occur in pairs, and that's where the one handles are attached. So here, so in this case, for the Poincare homology sphere, I got two one handles that are attached, a blue and a red. And again, this metaphor using a Pringle can, the ends of the Pringle can, the top and the bottom, are what is being glued to these disk regions. Um, so we're inside the zero handle, and outside of us, we're going to attach this one handle here, where one end goes to is glued onto this disk region. The other end of that Pringle can is glued onto this disk region, and that gives you a handle that you're adding on, a one handle, a three-dimensional one handle. Same thing for blue, red down here. Uh, it, uh, it's two disk regions where I'm gluing in on one handle. Now the thing is that I want to record information inside these disk regions, and the information that's inside the disk region is identical, except that it's reflected. All right, so this is why I'm calling this guy V1 minus and V1 plus. And down here, this is V1 minus and V1 plus. Uh, so uh, so the co-core of these one handles, it's oriented, and the core of the one handle is oriented, and it's all right-handedly oriented. And so uh, this end right here, the negative end, is oriented in a clockwise direction, and the positive end is oriented in a counterclockwise direction as we stare out at it. And I've got edges coming out of it. Now, what the edges are is the attaching information for the two handles. You look at the two handles, and again, like I said, they're a tuna can, and you're gluing the label in. But what you actually only need to do is specify the core of that label, that annular core, that core of that annulus, which is the label, and it's oriented too, and it's a boundary of a two disc that's inside the two handle. And so I've got an orange and a black, and you just pick a spot, and I've got the orange going here. It goes backwards over this blue one handle, and it goes from 4 to 4 here, and then it comes out, and it goes forward over this red one handle. It goes forward over the one handle from 7 to 7, and it comes out, and then it goes back up here to 5, and it goes forward over the blue handle, and you just trace it out. And you can similarly trace out what's going on for the black. All right. So that right there is enough to give you a description of the handle decomposition. Handle decomposition for your three manifold there, this Haggard graph. And it is in fact equivalent to the information that you would have from the Haggard splitting, but it's just this planar graph. All right. So we're going to put we're going to want to put your knot into normal position with respect to the um, handle decomposition of your three manifold. And so when you do that, what does that mean, normal position? Well, that means that once you put it in that position, the handle decomposition for the three manifold imposes a handle decomposition for your one manifold. And the handle decomposition for any one manifold, which are just copies of S1s, is just going to be, there's only two types of handles, a zero handle and a one handle, because that's just the one handle is the highest dimension of a one manifold. And the zero handles are going to be positioned inside the zero handle of your three manifold. The one handles of your knot components of your knot link, they are going to go through the one handles of your three manifolds, and all you have to do is specify an endpoint, a point on either end of your Pringle can. If you specify, let me do it here. If you specify a point here, then that's like specifying a point here, and then you cross it with I, and it goes straight through, and its reflection appears over here. So it's like between 2 and 3 there. It'd be right there, say. All right. So all you have to do is specify a point, and then you cross it with I, and you get the normal position of the one handle of your one manifold inside these three-dimensional one handles. And then outside, it's just it just comes out, and it's some arc that's tangled or whatever, and I can that would be a crossing. I didn't draw the over and under crossing, but that's what you would be doing. Um, and let's see. Um, so that's the structure that you want on the link that you're putting inside uh, the um, um, the th- um, the three manifold. Now we're going to want to I'll give you an example here of one. Well, the easiest ones to describe is you just take uh, the core of your two one handles, and you extend them into the zero handle, and you get yourself a loop. So this light baby blue loop is a zero handle that's out here in zero handle of that S1 that's out here in the zero handle of your three manifold, and then it goes into the one handle and back. And you would orient this, and I'm going to most likely I'll choose the orientation that corresponds to the orientation of the one handle. And you do the same thing down here. Here's another way. You just take that core and you extend it into the one handle down here. And so I end up getting a link uh, that when you restrict it to the zero handle, it becomes an entangle. All right, so this is a two tangle up here. Um, and um, and the only condition that you have is that the endpoints that appear in these fat vertex disk regions, their reflection be identical across. And so you may have a tangle that has a bunch of points here, then you see the reflection of a bunch of points here, and they'd be all strands inside the zero handle. Okay, so the normal position for the two manifold, the surface that we're going to want this to be the spanning surface of your link. We want it to be made up of. It will be made up of 0, 1, and 2 handles, and 2 is the highest dimensional handle that you can have for a two manifold. All right. And those 0, 1, and 2 handles are going to be in normal position with respect to the handle decomposition of your 3 manifold. All right. So the zero handles are going to have are going to be properly positioned. Zero handles of your surface are going to be properly positioned inside the zero handle of your 3 manifold, which means what? Which means they're going to all be disks with their boundaries on the boundary of that zero handle. Um, all the 1 handles are going to be have the structure of B1 cross B1, and they are going to be disks that are properly embedded. I'll put air quotes around that because I have to explain a little bit. Inside the 1 handles, and all your 2 handles are going to be have the structure of a B2 cross 0. That's their structure. And they will be inside the 2 handles of your decomposition. So if you go back let me go back to the one before. So the one, so we're, you'll have 0 handles for your surface. It'll be some curve, there'll be some simple closed curve on the boundary of your 0 handle, and it'll bound the disk that's coming into us. Again, the viewpoint that you should have here is that we are sitting inside the 0 handle of the 3 manifold. And then the 1 handles, um, I'll augment this. Maybe I should actually draw a bigger one. The 1 handles, here's your Pringle can. It'll be large. So this is a 1 handle, a 3-dimensional 1 handle. All right. Now, the 1 handles of your surface, all I have to do is specify an arc or an arc, and then cross it with the I structure of your 2 handle, and that gives me the 1 handle that I will want for uh, the the surface that I'm building, the spanning surface. That isn't quite cross-eye. My finger is wavering here, but all you do is take an arc here, specify an arc. You can do it on either end. You specify an arc, and then you cross it with I. And when you do that, it has the property that whatever arcs you draw over here, they appear over here except reflected. Okay. So let's go forward. So and then the 2 handles for the surface, they're going to be parallel copies of the core of your tuna cans, of your 2 disc. So here is your 2 handle. It's a little flat disc, and this is a 3-dimensional 2 handle, and the 2 handles for the surface are just going to be parallel copies of the core disk inside here. All right. And then you have the twisting bands. So the twisting bands kind of occur last, all right, in each case. So that's the normal surface that we're going to go for. So this fact that I'm adding the twisting bands at the very end here, uh, these twisting bands, well, they're handles too, but they are not going through any one handle of your 3 manifold. In the case of the original Seifert algorithm, there are no 1 handles, and they're just sitting very close to the boundary. So you end up with a surface in this construction. You end up with a surface that's not in normal position with respect to the handle decomposition of your 3 manifold. It's within um, it's pseudo-normal because you have to add in these half twist bands that are very close to this to the surface. All right, so I got to do a little algebra homology calculation here, and you can rapidly read off once you have one of these Hagar diagrams, you can rapidly read off a group presentation for your homologies of the three manifold, because what you do is you take the cores of your one handles, and again you extend them into your zero handle, and you get a loop that goes around. I showed those loops before, and you get a loop that goes around, and those loops, they're oriented, and the orientation is coming from the orientation of the core of the one handles here. They are going to be the generators of homology. Now, to get the relationship, the relators for homology, you just trace out, you transcribe what you're doing with the attaching maps for the boundary of the core of your two handles, the orange curve and the black curve, and you trace it out and you transcribe it, but algebraically. So you say to yourself, well, I go over the blue handle algebraically so many times for orange, and I go over the red handle algebraically so many times for the orange, and you do the same thing for the black. And if you work it out for Poincare homology sphere, it turns out that you've got just two generators, because we've just got two one handles, and then the relators, there's just two of them because we got two handles, and the black I think this is a black relator. No, this is the orange relator. It goes over the um, uh, blue uh, one handle exactly minus one times, and goes over the red one handle algebraically twice, and then the black handle goes over the black one handle goes over the blue black two handle goes over the blue one handle algebraically minus two times, and then it goes over the red one handle algebraically three times. So you end up with these two relators, and that right there is a representation of the homology for the Poincare homology sphere. Um, the thing is, though, I don't know why that angle didn't work out. The thing is, though, the Poincare homology sphere is a homology sphere. So, in fact, what you can do is you can do some algebra, and you can see that each generator can be written as a linear combination of the relators. And that's what gives you that, you're talking about a homology sphere. So in fact, this is going to tell you exactly what you want to know for how to construct your surface. This means that three times the boundary of the co-core of of the handle associated with R1 minus two times the boundary of the core of the core associated with the handle R2. That is homologous to this, to the generator A1, and similar for A2. Um, so um, so the way the algebra works is you go off and use your handle decomposition to give you the um, uh, the homology presentation, and then if you are in a homology sphere, then you take your knot in normal position, So it's it's contained in the zero handles and one handles of the handle decomposition of your three manifold. It's positioned there, and the homology class that it represents can be written as a linear combination of the relators. And there'll be G relators because there's G two handles. And it'll be an integral solution to this. All right. And what we do as a result of solving this equation right here, I'm going to let L1 be the oriented loop that is parallel to the boundary of the two-handle core that's associated with the R1 relator. All right, so the R1 relator is generated by a particular the ith two handle, and if you take its the boundary of its core, that will be L1. And in fact, what we're going to do is we're going to push it that L1 a little bit into the zero and the one handles, and then you end up with a link because you take your original knot K that you're trying to figure out what the produce a Seifert surface, a spanning surface for it, and you take disjoint copies, X1 disjoint copies of minus L1. L1 is the link that's associated with the R1 relator that is just the boundary of the core of that two-handle disc, and I'm going to have it pushed into your zero handles and one handles, and you do that for each one. So I take X1 of these guys, the L1's X2 minus X2 of the L2s up to XG of the minus the LG, and you're positioning it all in the zero handle, one handle. This right here is homologically trivial. The class of this of the entire L is homologically trivial, which means inside inside the zero and the one handle, which means that it bounds a surface. All right. What we do then is we take the tangle that corresponds to taking this L and intersecting it with the zero handle, and we project it onto the boundary. Then we perform, and I put air quotes around it so because you're gonna have to do a little bit more, but we perform Seifert's algorithm on the projection of this tangle onto the boundary. And I'm gonna work it out for computing the Seifert surface for the A2 curve that is associated with that generator inside the Poincare sphere. And so A2 is again it minus negative twice the first relator plus once the second relator is equal to zero. So that means I can take two copies of L1 that's associated with the first relator and one copy of L2, and I'm going to change the orientation of the L1 curves such that it's negative. And if you look at those fat vertex, then you're going to have those knots, the L2 knots being dots here. These may not all be L1 and L2. This is both L1 and L2. I'm not going to distinguish. And on the other side, you're on the other paired fat vertex, you see the same thing. And since it's algebraically zero up here, some of the orientation of these dots, some are going into over the handle positively, and some are going over handle negatively. And since you've got that it's homologically trivial, then these guys are going to add up to 0. And down here for V2, this is where that the A1 is. It goes around, it's the extended core. You almost have the same thing that you have up here, except they add up to -1, and the +1 that you get is coming from the curve itself. So these all add up to -1. But then what you can do is um, I can pair these dots up. This will be so this is a dot that's positive, and this is a dot that's negative, and I can put an arc across there, and that corresponds to a one handle, because over here you'll see the its reflection. It'd probably be right here. And then you do the same thing. You put this over here and you see its reflection over here. And you do it here and you see its reflection over here. And so these are one handles that you're putting into the one handle. All right. And you do the same thing down here. One of these is going to be paired up with this guy. One of these is going to be paired up with this guy. And one of these is going to be paired up with that. I did that wrong. Oh, don't ask. What happened? Don't ask. I did that wrong, but I'm running out of time here. Let's do that wrong. All right. I think I got to stop this. It didn't clear. Let's clear it. Clear all drawings. It didn't clear it. Now let's go to the next one. All right, so you do that, and you end up getting a bunch of curves that look like this, except there will be one crossing here. All right, and these curves are actually pushed into the are projected onto the boundary. If you throw away momentarily, if you throw away your Haggard graph, it looks like this. And here's this one crossing. I'm going to smooth that crossing, and then I get a bunch of disjoint simple closed curves. They're all oriented. Now we're doing Seifert's algorithm now. We cap these guys off with disks. All right. Then when you when you cap these off with this, you cap them off with disks, and then you add in that one crossing right here, and that gives you a Seifert surface inside the 0 handle. All right, but you're now gluing on one handles on that go through the one handles of your 3 manifold to the underside of that Seifert surface. And once you do that, then you'll have its boundary being all those LIs. But those LIs are parallel copies of the cores of your 2-handle cores, and you can cap those off with parallel disks inside your 2-handle cores. All right. So it's a simple calculation. If you're interested, you can actually calculate what the surface is that you end up getting. There's like 6 circles here. There will be 9 one handles that go through the one handles of your 3 manifold, and then the 10th one comes from that added twisting band there. And then there's 3 2 handles that we added because we needed 2 negative parallel copies in one of the handles, the R1 handle, and we needed 1 copy of the core of the R2 handle. And you add that up, and we're looking at a -1 Euler characteristic, which means that A1 bound that a once punctured torus. And this appears in the current edition of Knot Theory and the Ramifications. Just to mention two references, I borrowed that one sequence of the Seifert's algorithm that I performed on the figure 8. I borrowed that from this 2006 paper that appeared in the transactions, IEE transactions on visualization and computer graphics, entitled Visualization Seifert Surface. Apparently engineers are interested in this. And then I mentioned before that the presentation of the Poincare homology sphere, that Haggard diagram comes from Dale Rolfson's paper, book. So again, thank you to the organizers, and happy birthday, 80th birthday to Lou Kaufman.